Okay, so is it recording?
Yeah.
Excellent. So before going into the details of the lecture today, I just want to share two images. This is one of your TAs, Kayla. She is so excited. Anybody know why she's so excited? She got to do homework. She's been waiting years for homework. And she's always been sad that her older brother Kim has gotten to bring home problems to do, and she hasn't had any. Rather than watching movies, she went straight and started doing her homework. She was rewarded later. So if people want an ice cream party later in the semester to celebrate doing homework on time and working on homework throughout the week, Kayla is up for it, and I will make it happen. All right, so I've played a bunch of songs from Buddy Holly, Richie Valens, and only one from the Big Bopper. If you actually want to hear the entire songs, I have collected the links over here on YouTube, so you can go look at them. This link over here will be hopefully to a song you've heard, and that will make more sense as the lecture progresses. So the first is, I want to show you three people, and I want you to tell me who they are if you can, and why I'm showing these three people. Anybody know who any of these three people are? I'm sorry, TJ, yes. I didn't realize you were on such good terms with him. And who is TJ? Thomas Jefferson. All right, can you start passing these around? So there's not going to be enough for anybody. The people in the left corner, we don't like you as much. All right, so which one is TJ?
Center.
Center. Who are the other two? Yes.
John Adams.
Johnny Adams, yes. And who's the last one? Last one is James Monroe. I know there's at least one history major in the class who should be able to help us on stuff like this. Now, there are there is a president who did go to Williams College, James Garfield. At some point in the semester, I might talk about his contributions in mathematics, which are at least mentionable. Why am I listing these three people? Anybody know why these three are listed? I'm sorry? It's got to be all three of them. Anybody know now? They all died on the same day, July 4th. Interestingly, John Adams and Thomas Jefferson died on the 50th anniversary of the signing of the Declaration of Independence. I forget which one died first, but the other one was uttering on his deathbed. Well, at least the other one is still alive. And basically, this is before Twitter and all this stuff is being updated live. Did not realize his great friend and colleague had died. Who are these two people? Yes.
Truman is on the left.
Truman is on the left. Yes.
Ford on the right.
Ford on the right. The only person to serve as president who is not elected president or vice president. Why are these two people listed?
Born on the same day.
Nope. Try again. Died on the same day. Ooh. Yes. They both died on December 26th. So when I was preparing this lecture, my family told me that this was a little bit morbid to be focusing on people who died at the same time. So rather than doing a problem like that, which we will get to later in the semester, we'll talk about the birthday problem. So how many of you have heard of the birthday problem before? If you've heard of, wow, okay. Is this I want to ask if this is because you're reading the book. So this could throw off a little bit some of the clicker data. But so if you haven't done the birthday problem before, if you don't know what the answer is and you have a clicker, I'm not sure if those two will be compatible, how large must n be before there's at least a 50% chance that I have two people in a room that share a birthday? If I have 5 people who share a birthday, I win. If I have 4 pairs of 2 sharing a birthday, I win. I want to just make sure that there's at least 2 people that share a birthday. All right, does everybody understand the problem? Are there any conditions or assumptions we should make? Yes?
An even distribution of birthdays.
An even distribution of birthdays. My wife is an identical twin. This is not a challenging problem on family gatherings on her side. Anything else we want to assume? Yes?
It's a random selection of people.
So one is that it's a random selection. We'll talk a little bit more about that later. There's another one that's it's related to uniform distribution of birthdays. And we'll leave it to the biologists to talk about how reasonable that is. What else do I want to assume?
Oh, they're not born on February.
Yes. Is there anybody in this class who was born on February 29th? I have a deal with admissions. They're not supposed to let anybody take my class if they were born on February 29th, because it makes this problem a lot harder to analyze. Because not all days of the year are now equally likely. So we will assume every day is equally likely. There's 365 days in a year. All right, so I'm going to open the polling. And so press A if you think it's around 11 people, B 22, C 33, D 44, and so on and so on. If you've seen this before, please don't vote. Okay? So I will give it another 10 seconds. So we're already up to 9 votes. All right? So roughly how many people do you need? All right, 5, 4, 3, 2, 1. All right, so nobody said A, 40% said B, 30% said C, 10% said D, 10% said E, and 10% said I, which I don't think is an option. Okay, so if you hit I, that means you want to take my complex analysis class where we study things like I all the time. All right, I was going, that doesn't add up to 100%. So you want to do quick calculations to see if answers are reasonable. So why can we eliminate I as a possibility? It's not listed, okay. Anything else we can immediately eliminate in the words of Monty Python is right out. H. Why is H right out? Yeah, pigeonhole principle. There's 365 days. If nobody's sharing a birthday, once I have 366 people in the room, have to have a birthday shared. All right, so H is right out. What about G? Possible, but extremely unlikely that G is going to work. What about F? Imagine you have 179 people and nobody shares a birthday. What's the probability that somebody walks in and shares a birthday, roughly? It's about a half. So in some sense, 180 might seem reasonable, because if you get to this stage, when the next person walks in, there's about a 50-50 chance. The problem is for those few ones right before 180, 179, 178, 177, 176, those are all about a half. So the probability that you haven't had a conflux of 2 people sharing a birthday by the time you're here is very small. Similarly, around 90, your probability of sharing a birthday is roughly about a fourth. So if you want to look at what's the probability that no one is sharing a birthday, well, when people are coming in, they've got about a 3/4 chance of not sharing birthdays with the people before each other. And so as you start multiplying that out, you'll see 90 is probably too high. It's probably one of these numbers. All right, so it's mandatory. We have to do the birthday problem here. All right. One of the nice things about having this many students is I am not even remotely worried. Ice cream is on me if people do not share a birthday. January 21.
September 29. August.
I'm sorry, do we already have a hit? Oh, no, okay.
August 2nd. May 26th.
Oh, September 18th, October 31st, October 13th.
February 10th.
April 28th.
October 7th.
August 27th.
January 17th.
April 17th,
July 20th.
If somebody has your birthday, shout it out. January 29th?
May 18th.
Wait, okay, we have that? All right, so
Not 29, just 9.
oh, January 9? But you two seem to have misheard and so. Okay. So it's a 13-week semester, right? It's or 12 weeks. I'm trying to see how long this class is going to be. All right. I'm not going to go through and just see how many matches we have, but we didn't even have to get to all the people in the class before we got a match. Never had this one happen before. My favorite was my first year at Williams. I was doing this in a Calc 1 class, and it wasn't until the last or the second to last row that I got a match, and it was 2 people who were friends sitting next to each other. So I'm very confident in something like this that I'm going to get a match. And what you can do is you can plot, and I'll show you in a few minutes how you actually get this plot of what's the probability that you share a birthday based on the number of people in the room. And if you look at this, around 23 or so is where you get that 50%. Now, one of the things we do in math all the time is we generalize. Whoops. Okay, so let's imagine we move to Pluto. I am not going to get into a discussion as to whether or not Pluto should be considered a planet or its new downgraded status as a dwarf planet. I actually know somebody who knows the person who pushed the button to physically downgrade Pluto. My kids are still upset about this. That is outside the jurisdiction of this class. But what I can do is I can ask, well, what would happen if we were to replay this game on Pluto? And now, let's, I'm just adding roughly zeros. Now I is actually a legitimate opportunity. We have, say, 90,520 days in a Plutonian year. So we knew, if we looked at that plot, if we were on Earth, it would take around 23 days. How do things change as we get larger? And so in the interest of time, I'm not going to go through the whole calculation. I'm going to just plot the curve. The curve functionally looks very similar to what we saw before. Did I go backwards? I went backwards. That's probably why it looks so similar to what we had before. But even if we go in Plutonian, it still looks pretty similar. Can anybody look at this and quickly see roughly what the answer should be? Let's see, if this is about 50% over here, coming down over here, maybe around the 333. If I want to just quickly look at this. So the natural question becomes, as I vary the number of days in the year, how does the answer vary? This is going to allow us to talk about notation. How do you write things down in such a way to make the calculations easy to follow as you do a lot of painful algebra? How do you generalize a problem? How do you see parameter dependence? It turns out that the birthday problem actually has applications in cryptography. This is what's called the birthday attack on various things. So this is not just a cookbook example. Right. So what I want to do is I want to start talking about some quantities. And we had a little bit of an issue with this, I think, on the first day of class. Pn and Q1, they're going to be complementary probabilities. So Pn is the probability at least two people share a birthday when we have n in a room. Q1 is the probability that there are no shared birthdays when n is in a room. What's the relationship we should have between P and Q? They should sum to 1. Or equivalently, Qn is 1 minus Pn. So oftentimes it is easier to calculate one than the other. If you don't have much experience, what do you do? I'm sorry? I can't hear you.
Look for Pn.
So look for Pn, and what if that becomes painful? Look for Qn. So if you don't know ahead of time which one is easier, start doing one of them. If the calculation is going well, great. If the calculation is not going well, stop and try the other. This is one of the most important concepts in probability. It's the law of complementary events. That frequently it's easier to calculate one than the other, so try to find which one is easier. All right. Now the next thing is, what is the correct model? So we talked about a lot of these issues when we were describing the birthday problem. We want to assume all days are equally likely. We want to assume nobody's born on February 29th. We want to assume it's a random sample. So in the textbook for the class, I have a beautiful passage from Malcolm Gladwell where he goes and he takes the Canadian Junior Hockey Championship game and he replaces the names of the players with their birthdays. And so you see March 11 starts off on one side, passes to January 4, passes to January 22nd, flips it back to March 12, who shoots point blank against Tigers goalie April 27, April 27 blocks, rebounded by Vancouver's March 6, shoots Medicine Hat defenseman February 9 and February 14 dive to block the puck while January 10 looks on helplessly, March 6 scores. Hopefully you notice something about these dates. What do you notice?
They're all early in the year.
They are all early in the year. Why?
The cutoff date's January 1st for hockey.
Yeah, a lot of times the cutoff date is January 1st. Do you want to just make the cutoff for a league, or do you want to just miss? You want to just miss. Because odds are, especially when you're a little kid, if you just miss, you're going to be one of the biggest kids that's left. And if you're bigger, you will have a competitive advantage. You'll play better. If you play better, the coach gives you more time, gives you more resources, and it just propagates. And so there's a wonderful passage that we are losing a lot of great hockey players because of stuff like this. And of course, we do care more than just about hockey. But this idea that you could be missing a large segment of a talented pool is extremely valuable. And that what might seem like a random sample is not necessarily a random sample. The reason I chose Buddy Holly, Richie Valens, and the Big Bopper is they all died on the same day. For those of you who had never heard that they died on the same day, is this surprising that they all died on February 3rd? Does it seem surprising? In fact, I hate to break this to you, but 3 of you in this class are all going to die on the same day. Why might it be surprising, or why might it not be surprising that all 3 of them died on the same day? Yes?
Should it not be surprising? It's just the birthday problem.
Well, but it comes down to, and this is an extremely important issue, and again, this is what I want to do in lectures. I don't want to do too much algebra in lectures. I assume by now you can do algebra and you do not want to see me doing algebra in public. I want to talk about the big picture and thinking about the key ideas. If I tell you ahead of time which 3 people die, versus just, I can look at all the musicians in history, and then I choose the ones together that all died at the same time. I have a much better chance if I can look at all the musicians and then choose which ones I want to present to you. Now, if I'm looking at US presidents, there aren't that many US presidents. I'm on the order of 40. But that's still more than the birthday problem, requiring around 23. So I would expect several people to be dying. Now, the fact that John Adams and Thomas Jefferson, 2 of our founders, who were instrumental, they were part of the Committee of 5 writing the Declaration of Independence, that they die on the 50th anniversary, that might begin to mean something. But for the Ritchie Valens, Big Bopper, and Buddy Holly all dying on the same day, there is another explanation. It was a plane crash. They were on tour. The bus was uncomfortable. It was unheated. It was long driving. Buddy Holly said, to hell with this, and he chartered a plane. And he allowed, there was space for 2 other people, and so Ritchie Valens and the Big Bopper went on the plane with him, and they had, sadly, an inexperienced pilot. They believe this is due to pilot error. So if you have 3 people and the plane goes down, not surprising, the deaths are going to be highly correlated. So the question is, what's an independent event? This is going to be a huge issue. The analysis is a lot easier if things are independent. How many of you have heard the song "The Day the Music Died"? That's about the plane crash here, and the other link was to that. All right, so let's try to calculate the probability that there's no shared birthday in the room. So it's much easier to calculate the probability that something doesn't happen, and then calculate the probability that it happens as 1 minus. And the reason is, if I want to calculate the probability that at least 2 people share a birthday, oh crap, I could have 2 pairs of 2. I could have a triple of 3. I could have a quadruple of, and a double. There's so many different ways I could have at least 1 shared birthday. It's much easier to calculate the probability that there's no shared birthday and subtract. So if I want to calculate that nobody shares a birthday and there's just 1 person in the room, this is not a bad problem. The probability is just 1. Now the next person walks in. And we want to calculate what's the probability that there's no shared birthday. Well, I'm going to first of all rewrite the 1 in a more enlightening manner. And I'm going to write it as 365 over 365. I have 365 possible dates for the first person. Any of those dates is possible. When the next person walks in, how many dates are available for their birthday? If I don't want to share. 364. So it's going to be multiplicative. The probability that the first 2 people don't share a birthday is going to be 365 over 365 times 364 over 365. And if we just keep going, if I wanted 3 people, I would then multiply by 363 over 365. And if I want to have n people don't share a birthday, what's the last one going to be? Excellent, minus n minus 1. And you should be doing something with your hands like this. Okay. And so all the way going down like this. And the reason we want to put the n minus 1, I just realized I forgot to take out the m&ms. The reason we want to put the n minus 1 in parentheses is to remind ourselves we start off, unfortunately, with the subtracting 0. We go all the way down to subtracting n minus 1. It's a little bit annoying just the way the bookkeeping goes for this, but not a huge deal. All right, so we can rewrite this in a more compact notation as a product, k goes from 0 to n minus 1 of 1 minus k over 365. And again, one of the big themes of this class is how do you look at algebra in an illuminating, enlightening way. How many of you have seen product notation like this? Okay, excellent. So I want you to have a Pavlovian response. I know some of you have taken a class with me, and I know you're probably fighting hard to restrain yourself from saying something right now because you've been so well trained. Whatever you see a product, what should you be doing? What should you be thinking of doing? logs. The only exception is maybe if you're teaching little kids multiplication tables. Try to resist maybe in that situation. Okay? Otherwise, if you see a product, you should be taking a logarithm. Why? To turn into sum. How many of you have taken Calc 2 and done integration and dealt with Riemann sums? We have a nice theory of summation. How many of you have ever dealt with theories of products? You could develop a theory of products, but we have experience with sums, so let's convert it to something we understand. And so if we see a product, we take a logarithm. So instead of studying Qn, we'll study the log of Qn, and the log of a product is the sum of the logarithms. And so we have this beautiful expression here. Am I still focused in the camera?
Yeah, you're in the view.
Excellent. And now, instead of doing this with 365 days in the year, we could do this with d days in the year. And the analysis is going to be almost identical. What would I change if I want to do d days in a year? Yeah, I would replace the 365 with a d. Not a huge deal. Now, I'm also replacing Qn with Qn of d. Notation is important. And there's a balance between having your notation so detailed that you can glance down and see what's going on, to I'm going to spend 15 hours of my life writing things down because the notation is so cumbersome. Here, to me, it's not that big of a deal to put parentheses d in and now know that my quantity Qn is varying with d. And as I vary d, I'm going to get different values for Qn. Now I want to understand the sum of the log of 1 minus k over d. Anybody know how we can understand the sum of the logs? So how would we deal with the sum of the logs?
Write a Taylor expansion.
So write a Taylor expansion. One thing you could do say is, well, the sum of the logs is the product. Well, if I do that, I just go back to where I was. And so that's not going to be that helpful. Another thing you could do is you could use calculus. And then I would want to basically be integrating this function. The sum of the log is going to be like an integral. The hope is that the value of n should hopefully be small relative to d. And if it's small relative to d, then this 1 minus k over d should be small. This should be approximately the log of 1. What is the log of 1? 0. So that this should be a small number. And hopefully the higher terms in the Taylor series expansion won't matter. So hopefully they told you why you were learning calculus. One of the big reasons you learn calculus is to linearize the nonlinear. I am really good working with straight lines and linear functions. Not so good as I start getting into more complicated functions in terms of solving, sine of x equals x, much, much harder to do. So the idea is if you can replace a complicated function with a linear function, you can often do enormous things. Well, the log of 1 minus u, if I calculate its Taylor series expansion, it's negative u minus u squared over 2 minus u cubed over 3, etc., etc., etc. If u is really small, then u squared over 2 and all this extra stuff over here is insignificant relative to the u. And I can say, the log of 1 minus u is approximately negative u. All right, now that I have that, I can feed that in. And we get the log of Qn of d is going to be the sum of the log of 1 minus k over d. Now I replace this using the Taylor series. And I have a sum of negative k over d. I'm just taking the first term in the Taylor series. If I wanted to do a better job, what should I do? Yeah, keep the u squared over 2 term. And you can actually see how much of a difference does it make, how much of a change. You will see in a few minutes why I'm not bothering doing the u squared over 2. This does a great job by itself. Well, I can pull out the negative 1 over d, and I have a sum k goes from 0 to n minus 1 of k. How many of you have seen this sum before? Okay, so this is an extremely famous sum. It's equal to n minus 1 times n over 2. One way to see this is I have the numbers from 0 to k, and I write the numbers 0, 1, 2, 3, 4, all the way up to k, and then write them in the opposite order, k, k minus 1, k minus 2, all the way down to 0. And if you write it like that, underneath the k you have 0, underneath the 1 you have k minus 1, underneath the 2 you have k minus 2. If you now add up like that, everything adds up to k. I'm sorry, I shouldn't be doing k, I should be doing n minus 1, sorry. So what you can see is, instead of doing this as an n minus 1, I'll go from 0 to n minus 1, then I go from n minus 1 down to 0. Each thing adds up to n minus 1. I have n copies of this, so I have n minus 1 times n, but that's twice my sum. So the actual sum is going to be half that. Right? So we might talk more about some of these sums later. How many of you have seen proofs by induction? So if you've seen proofs by induction, proving this formula by induction, that's one of the standard homework assignments. There's also formulas for the sums of k squared, k cubed, k to the fourth. They sometimes prove formulas like this in a Calc 2 class to just show you that the area under the curve is given by the antiderivative at b minus the antiderivative at a. You try to check this for straight lines, parabolas, cubics, and whatnot. And so then you have to evaluate sums like k, k squared, k cubed. So anyways, however you do this, you get that this sum is n minus 1 n over 2. To make my life a little bit easier, I'm going to just approximate this as n minus a half squared over 2. Why am I going to approximate it as n minus a half squared? Is that a reasonable thing to do? If I expand things out, I've got n squared minus n, I've got n squared minus twice 1/2 n, okay, n squared minus n, and I get an extra plus a quarter. So this is larger than this by just a quarter, but in terms of solving for things, I no longer have the quadratic formula to use. I now have a perfect square here. So this makes my life a little bit easier in terms of doing the algebra. I don't need to do this. I like the quadratic formula, but I'm already making approximations. This is not going to really change things that much when n is of modest size. All right, so now let's let n 1/2 semicolon d be the value so that the probability is 1/2. And again, this is the advantage of good notation. I'm looking for a special value of n so that the probability is 1/2. The 1/2 subscript means that that's the probability I want, and the d means that's how many days I have in the year. Not surprisingly, if I have a different number of days in the year, the special value of n is going to change. So now I have the log of 1/2 is equal to this quantity. The log of 1/2 is the same as, what's the other way of writing the log of 1/2? Negative log 2. And if I write this as negative log 2, the negative signs cancel. This is good. Whenever you're doing a complicated calculation, you always want to be asking, is my answer reasonable? What can you tell me about the number of days I need to have a 50% chance that two people share a birthday? What kind of number should it be? It should be positive. I should not get something like, I need negative 15 people in the room before I have a 50% chance. You might have been a little bit worried that we've got a negative sign that's floating around. Well, we have the log of a number less than 1. The log of a number less than 1 is negative, so the negatives will actually cancel and everything is on pace. This doesn't mean we haven't made an algebra mistake, but if you can keep doing checks like this throughout, you will minimize the chance of making a mistake. One of my former students was working in an investment fund and he actually did something like this and they had actually dropped a minus sign. And so it was very good that they did this before making a major investment. All right, well now what we can do is we can write this as negative log 2, the negatives cancel, I multiply it through by the 2d, I then take the square root and then I add a half and I get the following formula. So I get that the critical value is approximately the square root of d log 4 plus a half. So now if you vary d, I know roughly how it varies. It's going to vary like the square root of d. And so the assumption that n was much less than d is reasonable for modest values of d. We're talking about something on the order of square root of d rather than something of size d. You always want to go back and check and see, are your assumptions reasonable? This is a very reasonable assumption. Okay. If I found that the answer was comparable to d, then I would be very worried about using the Taylor series expansion because I was assuming k over d was small. But this is very warming. All right, so now we just do some algebra. We should take d equals 365, and we get 22.99, which is stupendously close to 23. It's actually a little bit better. It's 22.9944, I think. This is not a bad approximation. This shows you the power of calculus. We took a nonlinear function. We took a really bad product. How many of you have calculators? And by calculators, I mean calculators. I do not mean a phone that can calculate. I mean an actual physical calculator. Okay. So if you try to do factorials, if you try to do 365 factorial, your calculator will frequently blow up unless you have a really good one. The normal ones blow up somewhere between 60 factorial and maybe 88 factorial. When you want to do something like this, If we have these horrible formulas, you often have to play games about how do I multiply the numbers in such a way that I keep the quantities finite and in the range of the calculator. It's really nice when you can have formulas like this and convert these huge problems to much more manageable ones. So in the book I go through and I think I expand out all the different stuff. If you try to multiply the numerator and the denominators together, you can get very large numbers and you can deal with overflow errors. You've got to be multiplying and canceling as you go along. Okay. A big part of the class is going to be writing code. So I will be sharing with you the video on just basic Mathematica. Anything between star parentheses, parentheses star is just commented to make code more useful and more readable. How many of you have ever written code before? How many of you are good at commenting? Most of us are not good at writing comments in code. Sometimes there's a good reason for that. You want to be useful to the company. And if your code is very well commented, but you do want to get into the habit, if possible, of being kind, if not for the sake of the company, for the sake of yourself, if you need to look at it 2 or 3 years later. Now, why the hell do I have this line here? So you can get into the habit of writing comments. And by writing comments, I don't mean after the code is done, going back and putting the comments in. Write the comments as you're going along. Explain what you're doing. So here is some code as to how you would go through, and I'm basically doing multiplications. And I think I'm just keeping to do this until I get to a certain probability. And then I'm going to plot things out. So I'm not going to go into too much detail about how these lines of code work now. I will give a lecture on how to do coding. I don't want to do that on a day when a lot of people may be missing class. It's strange, it keeps moving backwards when I hit the first. I'm not going to go through this, but I'll just mention this one briefly. During the Democratic primaries in 2008, Clinton and Obama received exactly the same number of votes in Syracuse, New York. How probable was this? How many of you have heard of this event? So how likely do you think it is that they had the exact same number of votes in Syracuse, New York? Highly probable? Possible? Or extremely unlikely? And by exact, I mean exact. They don't differ by 1. They had exactly the same number of votes. Do you think this is likely? It depends on your model. Now, one of the things is, what am I telling you here? And this goes back to something we had with the birthday problem with the presidents or the musicians. Yes?
How many people voted?
So one thing is you want to know how many people. I want to say it was on the order of 12,000 votes. So about 6,000 for each. Did you hear that they also tied in Schenectady? Do you know the reason why you didn't hear that? They didn't. Did you hear that they tied in Albany? Why didn't you hear that? They didn't. Why do you think this makes the news? It seems newsworthy, right? There's a selection bias. In other news today, the following unlikely events did not happen. You've got to think about this. You want to talk about being able to use things in the rest of your life. What do you think is going to be reported to you? The unlikely events are going to be, well, if enough events are going on, you expect some unlikely events to be happening. So if I had told you before the voting happened that they were going to tie in Syracuse, that now means something. But when you look at all the places in America that were voting and all the sizes of the populations voting in the Democratic primary, for there to be a tie somewhere no longer seems so surprising. It's, do you specify this ahead of time? That's where the difference is. And then again, going into the different stuff, one of the questions you can have is, what's the probability? Do they each have a 50-50 chance of votes? Do you look at their total statewide vote totals? Do you look at just their vote totals in upstate New York, which is different than New York City? So depending on the model you use, the answer can be anywhere between 1 in 1,000 and 1 in a million. Okay, so what I want to do now is I want to go from shooting hoops to the geometric series formula. If I didn't have to go back and forth between 2 classes, I would have actually brought my basketball net and had us play a game of basketball. If anybody wants to, by all means, come to my office and we can play a game of hoops. How many of you have heard that this building is going to be torn down? Okay. My kids want to save two things in my office. One is the little mat, because my daughter likes to draw on it. It's a nice, good surface. And the other is the basketball net. So I can't guarantee that my Legos or anything else will be saved, but no matter where I go, I will have my basketball net. All right, I do not remember the musicians I played at the start of the class, but I do remember these two people. Who are they? Larry Bird and Magic Johnson. I know I should probably do Larry Bird and who remembers the famous commercials? The McDonald's commercials? Or the movie Space Jam? How many of you have not seen? How many of you have seen Space Jam? It should be Larry Bird and Michael Jordan. Yeah, they had the very famous series of commercials for McDonald's. Nothing but net. But when I grew up in basketball, there were only two teams: the Celtics and the Lakers. Every now and then there were the Sixers who would play the Celtics to determine who plays the Lakers. But basketball was very simple when I was a kid. And this was one of the greatest rivalries. Goes back to their college days. Larry Bird versus Magic Johnson. What we're going to do now is we're going to consider a very simplified game of hoops. Bird and Magic are going to alternate shooting. Larry Bird will shoot first because I am from Boston. And so I will give Bird the first shot. Bird will always make a basket with probability P. Magic will always make a basket with probability Q. You could replace this with P sub B and P sub M. And just have an extra symbol. And then not worry that a lot of times people pass Q as 1 minus P. In a paper that I've written, I actually did do this. I prefer not to have the subscripts and make it a little bit clearer to write. So there's no relation between P and Q here. I am assuming that they always make a basket with the same probability. Do you think this is reasonable? No. 90-year-old Larry Bird is probably not going to shoot as well as 25-year-old Larry Bird. Right? But, for a math class like this, I can make simplifying assumptions. So I'm going to let x be the probability that Bird wins. What is x? So can anybody give me a trivial bound on x? I think I saw your hand first. Between 0 and 1. I deserve that. Yes. Can you do a slightly better bound than 0 to 1? But you're absolutely correct. That is the first trivial bound you should give is between 0 and 1. There's a hand over here. Can you do better than 0 to 1? Good, you're all thinking very trivially. Between P and 1, right? If Bird makes a basket with probability P and Bird gets to shoot first, it's probably at least P. Does it have to be larger than P? No, why not? Yes. If Q is 1, if Magic is this basketball machine and always makes baskets, then it will just be P. All right, so we know, without even doing any calculations, x has to be between P and 1. That's not bad. So let's calculate the probability that Bird wins. So we're going to break this into cases. And this is, again, one of the common methods in probability. This is why I want to spend so much time in today's class going through these two problems. We see so many of the techniques that we're going to be returning to throughout the semester that it's worth going through these problems very slowly, very carefully. So Bird could win on his first shot, which happens with probability P. I want to break Bird winning into a bunch of mutually exclusive cases. Case 1, Bird wins on first shot. What's case 2?
Bird doesn't win, then Magic doesn't win, then Bird wins.
Good, so Bird wins on his second shot. What's the probability Bird wins on his second shot? Yes?
1 minus P times 1 minus Q.
Good, so Bird misses, Magic misses, and then Bird hits. So for Bird to win on his third shot, Bird misses, Magic misses, Bird misses, Magic misses, Bird hits. All right. So this is getting to be pretty straightforward. If I want to have Bird win on his nth shot, I'm going to have n minus 1 times of 1 minus P, 1 minus Q, 1 minus P, 1 minus P, and then a P. And so this would be the probability that Bird wins. I now just have to sum this infinite series. And this is going to be passing the event we want, Bird wins, into a bunch of mutually exclusive alternatives. Bird cannot win on his third shot and his 8th shot. Once Bird wins, the game is over. All right. So in order to simplify the writing, we're going to let R, apologize for the Boston accent, be 1 minus P times 1 minus Q. And so now I get the probability that bird wins is p plus r times p plus r squared times p plus r cubed times p. I get the following. This is the geometric series formula. Or at least this is the geometric series, and then I evaluate this using the geometric series formula. How many of you have seen the geometric series formula, the sum of 1 plus r squared? You should have seen the geometric series formula by now. Right? What I'm going to do is I'm going to show you a way to prove the geometric series formula from considering this game of hoops. So this is an alternate way to prove the geometric series formula. This is extremely important. This is one of the most important sums we have. The reason it's so important is we can evaluate in closed form. Most sums we cannot evaluate in closed form. So we want to evaluate the sum. Now the nice thing is, in general, r is going to be less than 1. What is the only way r could be 1? Yeah, if bird and magic never make a basket. What's the probability bird wins if neither bird nor magic can shoot for crap? 0, okay? I'm really not going to spend too much time analyzing what goes on when neither one of them can make a basket as to what's the chance of bird winning. So I'm going to exclude that case. So for me, at least one of p or q will be positive, which means r is going to be strictly less than 1. So r will be somewhere between 0 and a number less than 1. So I don't have to worry about the sum diverging. And because the sum converges, if you stop at a certain point, you can actually bound how much the remainder is, and it's not going to be too large. All right. So we showed the following. I'm just rewriting it. And now we're going to solve this without an infinite sum, without recourse to the geometric series formula. In fact, we're going to prove the geometric series formula. So what we're going to do is we're going to calculate the probability bird wins another way. How many of you have ever done any combinatorics, binomial coefficients, these counting games? Okay. We're going to do a lot of that throughout the semester. The secret to most of combinatorics is take what you want to do, and if it's hard, show that your problem is equivalent to something else that you know how to do. Count it 2 different ways, where one of the ways is hopefully significantly easier. That's basically the trick to all of combinatorics. Now the difficulty, of course, is finding that easier way. And so I will explain throughout the semester how can you view these combinatorial problems in a new light where the second calculation is much easier. All right. So let's calculate the probability bird wins. So that's x. Bird could win on his first shot. Now if bird is going to win and bird doesn't win on his first shot, what must happen on bird's first shot? He misses. What must happen on magic's first shot? He misses. All right. This is the $64,000 question. Don't answer if you've already seen this. Bird misses, magic misses. From this point onward, what is the probability bird wins? It's just like starting from the beginning. Once they've both missed, remember, bird doesn't tire, magic doesn't tire. This is the idealized Larry Bird. The probabilities do not change over time. Once they both miss, we've started the game all over. So what's the probability that bird wins once they both miss? X. What's the probability bird wins once bird misses? Is that also X? No, because you still have magic who has the ball. It's very important that I return to the initial configuration. The initial configuration was bird has the ball. So once bird misses, I'm not done. I have to let magic shoot. Basic fairness. And then once magic shoots, now bird has the ball again if magic has misses. I've started the game all over again. And so now they both miss, and then from this point onward, it's just X. Which would you rather solve, an infinite sum or a finite sum? So that's the power of something like this. This is a memoryless process. This is one of the most important concepts we have in mathematics. It's used all the time in economics, in game theory. How many of you have ever played chess? What's a way that a game in chess could end in a draw? Anybody know? I'm sorry? Stalemate, yeah. I mean, how could you, that's one way, but how can you get?
You can like keep moving like your kings like 50 times or something at the end.
There is a rule like that. There's a limiting rule. There's another rule.
Isn't a stalemate if
There is that. I have too many chess knowledgeable people. If you have a threefold repetition, I think, of board state, where the pieces are in the exact same configuration and it's the same person's turn, that's called a draw. Because there are some situations where you can go back and forth, back and forth. Well, if I stop this attack on you, you're going to attack me, so I'm going to do this. Well, I'm not going to. And you can actually have a draw in chess because of something like that. So there are lots of situations where you have a game which is memoryless. It doesn't matter how you got there. It just matters that you're there. Now in chess, you also have to keep track of how many times you've been in that state. That does matter a little bit. So there can be some subtleties. Well, this is a very basic algebra problem to solve. We're calling 1 minus p, 1 minus q equal to r. And so if we just do some basic algebra, we get 1 minus r times x is p, so x is p over 1 minus r. But what else? We know that x is equal to this infinite sum. Well, what can we deduce? I'm sorry? The formula for the geometric series. You have to say one more thing unless you want to be a physicist or even worse, an economist. We need one more thing if we want to say this equals that and get the formula for the infinite sum. Not quite r is less than 1. Nope. There is a way for these two to be equal, but the geometric series could fail. P is not 0. If p is equal to 0, I can put whatever I want over here. So if p is not 0, I can then deduce that these two must be the same. And now we get the infinite sum is equal to 1 over 1 minus r. There's the geometric series formula. Now typically, if you've seen a proof of the geometric series formula, they say this is true, bless you, if the absolute value of r is less than 1. Have we proven this if the absolute value of r is less than 1? No. What is preventing us from having that this is the absolute value of r is less than 1?
The probabilities that make up R are less than 1. So like R is equal to 1 minus p times 1 minus q. So
Okay.
those are both less than 1, so the multiplying must still be less than 1.
Right, but so does that mean that I've now proven this formula if the absolute value of r is less than 1?
So it doesn't include the negative cases?
It does include the negative cases. I'm dealing with probabilities. As bad as certain players are, you're not going to have a negative probability of making a basket. So this only proves the geometric series formula if r is positive or 0. If r is negative, you have to figure this out. Well, what you can do is you can note, well, if r is negative, r squared is positive, r to the 4th is positive, and then you can group things. And so I'll leave it as an exercise. You can actually get the formula for negative r just by knowing the formula for positive r and essentially using it twice. Okay, so there's a lot we can get from this. The power of perspective, this is a memoryless process. You can circumvent algebra and get a deeper understanding of what's going on. This is hard, but it's valuable. The depth of a problem is often not what it seems. It's not an infinite calculation. We could do it as a finite calculation. As a final aside, let me see the hands for those of you who have seen Space Jam. The first time my son watched this with me, he was very young, he was a big baseball fan, and the question he had was, will Michael Jordan ever play baseball again? So sometimes you may not always understand exactly what the point of the calculation you're doing is. And so for stuff like this, before you do a huge algebraic calculation, try to think, what am I trying to solve? Is there a better way? Is there a better path? What do I fundamentally care about? For this problem, do we care about doing the infinite sum? No, we just care about calculating the probability bird wins. How can we do it? One way is through the infinite sum, but maybe there's another way. So really think about what is it you're trying to do. Okay, this is a good place to stop.